So hello and welcome everyone. I am Jay Dalsaniya and in this video we are going to study the question rightmost different bit. So this question is very easy to understand. It has not got much complexity. So without wasting any time, let's start the video. So what is the question? First of all, let's try to understand what the question is trying to say. So in this question, you will be given two numbers m and n, and you have to find out the position of the rightmost different bit in the binary representation of the numbers. If both m and n are the same, then you have to written -1 in that scenario. Okay, so let's try to understand with this example go over here, which is given to us. So the value of m, let's have a look at the example. So if the value of m is equivalent to 11 and the value of n is equivalent to 9. So basically what you have to do, you have to find out the rightmost bit which is different in both of them. Okay, so first of all, what will be the binary representation of 11? It will be something like 1 0 1 1, 8 plus 2 plus 1, 9 11, right? And what will be the binary representation of the 9? It will be 1 0 0 and 1, right? So this is the right side of this binary representation. So one by one, let's compare which is the different bit. So this is same and this is different. So this is the first bit, this is the second bit. So the output for this test case comes out to be 2. So you have to print out which is the rightmost bit and which is the different one. And now let's take one more example for better understanding. So this was example 1 and example number 2. So let's take the example given in the question. It is m is equal to 52 and n is equal to 4. So m is equal to 52 and n is equivalent to 4. What will be the output? Let's have a look at the output. So before that, let's have the idea about the binary representation of 52 and binary representation of 4. So the binary representation of 52 is 1 1 0 1 0 0, and for this 4 it will be 1 0. It will be something like this, right? So one by one, let's have a look at the rightmost bit. So this is the first bit, similar, similar, similar. This is also same, and this bit is not same. So which is that bit? 1 2 3 4th and 5th. Fifth bit is not same. Basically they are different. So the output for this test case comes out to be 5. You can have a look at the quotient as well. Both the outputs are matching. So this is how you have to find out the rightmost different bit. So the question was not that difficult to understand. Now here comes how will you implement this part. And the implementation is also very easy. Basically the logical part is also very easy. And let's have a look at the logical part. So basically, first of all, what we need to understand, one thing we need to keep in mind before understanding the approach. So that thing is that any number, let's say a, if I do the logical AND operation with a, basically a and 1 will give you what? It will give you 1 or it will give you 0. So what will be the output? How can be the output be 1 and 0? So let's say if the value of a is equivalent to 8, that will be this 1, 3 times 0. And now if I do the AND operation with 1, so 1 will be this. And let's say 8 is what? This is your 8. So if you do the binary AND operation, you will be seeing that the output comes out to be 0. The output comes out to be 0. So basically that denotes that this last bit of 8 is equivalent to 0. If the output of AND operation with 1 is equivalent to 0, that means the last bit of 8 is 0. And now let's say if there was 9 instead of 8, and if I do AND with 1, you will see that the output comes out to be 1. So basically 1 will be the output whenever the last bit is 1, and 0 will be the output whenever the last bit is 0 of that number a. Right? So based on this property, what I will be doing, I'll be comparing the value of 8, basically the value of variables m and m. So what I'll be doing, I will keep on iterating. So basically, let's take an example. Let's say if the value of, let's say this example, 11 and 9. So let's say this is 11 and this is 9. So we know the binary representation of 11 is 1 0 1 1. And what is the binary representation of 9? It is equivalent to this 1 0 0 and 1. So now I will do that if the value of m and n, basically if the value of m and 1 is equivalent to the value of n and 1. So basically that denotes if the last bit is same, then what I will be doing, I will be deleting the last bit from both of them. So basically I'll check if the last bit is same, then I delete the last bit. So all the bits will be shifted to the right position by 1. Okay, so now let's do one by one. So I'll check if m and 1, so basically 11 and 1 and 9 and 1, what do you think will be the value? It will be 1, both of them. You can observe over here, and with 1, this will give you what? It will give you 1, and the AND operation with this one will also give you 1. So basically, what will be the output? The output comes out to be 1 in both the same, both the bits are same. So I will do the right shift of both of them. So I will do the right shift. M is equivalent to right shift by 1 and n is equal to right shift by 1. And along with that, one more thing I'll be using, that is the bit position. I'll be checking whichever bit is not equivalent at that position, what is that position. So basically I'll use one variable, position variable, and whenever I see the value of basically the bits are same, I'll increase the value of position by 1. Okay, and then I'll be doing the right shift. Okay, so this process will be continued each and every time until and unless both of them are having different bits, right? So now doing the right shift of both of them, so this bit will be discarded. So this is the entire remaining binary representation. So what is this binary representation? This binary representation now changes to, this is 1, 2 and 4, this is 5 and this is 4. So now doing the AND operation, again AND operation, 1 and AND, it will give you what? It will give you 1. Okay, so basically this thing we did, and now again with this 4, if I do 4 and 1, I'll be getting 0 in this scenario. So basically, let me write down over here. So if I do 5 and 1, I will be getting 1, and if I do 4 and 1, I will be getting 0. So over here, the value, this condition is not satisfied, that AND operation with 1 for m and m does not give you the same bit. So this is the thing where I will stop the iteration. This is the point where I'll stop the entire iteration and I'll just come out of this entire loop. And on coming out of this entire loop, I know that the value of this position variable has now been increased to 1. So I'll increase the value of position again by 1. And I will say that this is the position where both the bits are different. Okay, and what will be the value? The value comes out to be 2. So let me write down the entire algorithm in a clear manner so you can have a understanding. Position is equivalent to what? Initialized with 0. And now the value, I'll be using a while loop, while m and 1. And basically this is equivalent to n and 1. If this is the scenario, I will increment the value of my position variable and I'll do the right shift of m and n. So m right shifted by 1 and n will be right shifted by 1 as well. Okay, and at the end you simply need to do +1. You simply need to do the +1 with position and return it. Okay, so this is the entire algorithm. And now let's have a look with one more test case so you can have more understanding. So let's say both the values, let's say m in this scenario comes out to be 5 and n comes out to be 2. So binary representation of 5. What is binary representation of 5? It is 1, 0, 1. And for 2, it is this one, 0, 1, 0. So now I will do the operation m and 1. So m and 1 and n and 1. So what will be the value? It will be 1 for this scenario. It will be 0 for this. I can see the AND operation with 1 for m and n comes out to be different. So at that point, I know the value of position variable will be initialized to 0 and this loop will not be executed. Control comes out of the loop and I'll be returning position +1. So position +1 will be 1. So the first position from the right hand side is the place where both of them are having different values, different bits. So this is how the entire algorithm works. A simple iteration over the bits, and one by one you will be right shifting all the bits by one position. So basically this is the entire algorithm. Pretty simple algorithm and pretty straightforward. Two things only done. Basically AND with 1 and do the right shift. Okay. So now let's have a look at the implementation part. And before moving to the implementation part, try to guess what will be the time and space complexity in this scenario. So the time and space complexity depends upon which number is having more number of bits. Okay, so let's say if m and n, over here you can observe, let's say m is equivalent to 52 and n is equivalent to 1. So obviously this 52m will be having more number of bits. Okay, so the time complexity depends upon whoever is having maximum of log of m or log of n. Okay, so this is the entire time complexity. And what will be the space complexity? Space complexity is constant. Nothing fancy, nothing extra has been used. That depends upon the input test case size. Okay, so that was it for the entire algorithmic part. So now let's move to the implementation part. So over here I've implemented this entire thing in Java, but the same can be implemented using uh, other languages. Take the reference of the algorithm which I've shown. And now over here I have written down one more statement, that if m and n both of them are same, I'll be returning minus. So try to think on this statement. Do you guys agree? Let's say m and n both of them are having value 2. So both of them will be having same binary representation. So obviously it's not possible that any of the bit might be different in both of them. So I have handled that scenario over here in the beginning itself, and I'll be returning -1 over here itself, right? So now if you do not handle it over here, now you need to handle it differently over here in this while loop, because the while loop will keep on going infinitely. So this condition is very much important. Okay, so now I have used the position variable to denote the position, and now I'll be checking if m and 1 and n and 1 are equal or not. If they're not equal, then position variable will be increased and both of them will be done right shift by 1. This continues until the bits are different, and whenever the bits are different, the return statement position plus 1 will be executed. So let's try to submit the same, and let's try to have a look at the acceptance. And we can see that the problem has been successfully submitted. So that was it for in this video. I hope you really enjoyed the solution. So thank you for watching. I will be seeing you in the next video. Bye bye.